Thank you for the possibility to talk about EMTO. It has been a long time that I didn't talk about EMTO. It was developed long time ago, almost 25 years ago. Or when I started first time, it's more than 25 years ago. And they asked me to discuss today a little bit the fundamentals, implementation, and perhaps some demonstration of EMTO. I have a few collaborators with whom I started this implementation when I was postdoc in Denmark at DTU, Danish Technical University, in '98 with Hans Kriver, and then I continued in Uppsala. After I moved to KTH, I continued in 2000. After 2000, then they joined our group, Andreas, later on Henrik. These three young people, they contributed, especially they helped me a lot with cleaning the code. I'm not a programmer. I cannot make a very powerful and efficient programming, but they managed to do that. He also helped me to implement a full potential version of this code. I will not talk about that today, but we have that. Andreas worked on many body effects. You know, EMTO is a density functional tool, but we can go beyond DFT, and we did that with Andreas. And Henrik also had the contribution on different levels. So I don't know exactly the audience, so excuse me if I go to a little bit, start from the very beginning. It is called EMTO, exact Muffin-Tin Orbital Theory. And, you know, Ole Krogh Andersen, the person here, he was the researcher who developed Muffin-Tin orbital and especially linear Muffin-Tin orbital method in the 70s. You know, in the 80s, 70s and 80s, the most widely used density functional solver was LMTO, linear Muffin-Tin orbital method. Why? Because you could run on small computers. And in the 90s, he went further and developed the so-called exact Muffin-Tin orbital theory, which is not linearized. But then later on, they tried to make a kind of linearized or parameterized version, and they named it NMTO. To my best knowledge, there are no really good implementations of NMTO so far, but EMTO I took and I implemented with my friends. And if you want to read a little bit more about the background, you can find in this book and also in some publications. Of course, you can ask what is exact, and you can read here what I got in 2004 from one of the referees, that why do we call it exact? It's nothing exact in electronic structure methods, and that's true. Of course it's not exact. But compared to the formal Muffin-Tin type of implementations, there are many Muffin-Tin based implementations, we have some features, and this is why I point out here that the kinetic energy compared to what used to be in the old days, this is analytically exact, almost exact, not numerically, of course. And then the charge density is also almost exact, because we don't anymore apply any Muffin-Tin restriction to the charge density. I want to start with the density function theory because EMTO, the code, the computer program that you can access today, it is not only the EMTO theory itself, but it contains also the full charge density method. And without and then we have to start from the basics of DFT to understand. And you know, according to density function theory, the total energy of interacting electrons, you can write as a function of the density. And that's very, very important point, that if you know the density, the charge density, which is it's a function of three variables, x, y, z, position only in the 3D space, then you can give the energy. And this energy functional has a minimum for the true density. The true density that contains the same number of electrons. I mean, the number of electrons, of course, is fixed. So you can change the density, and then the total energy functional is minimized. So one could do that. And, you know, nowadays we don't talk, and those users do not very often talk about this. But in principle, if you had time, you could take this functional, play around, find any density, trial density, change it, and minimize the total energy. And then you find minimize the total energy functional, and then you find the total energy of the system. And variational, that means that the functional derivative vanishes, right? I don't write it here on this page, but the first order derivative of the density functional vanishes. And that also brings something into it, that if you come pretty close to with the density to the true density, then your error in the total energy will be of the second order. Because of that, remember this, please. It's very important. Whenever you do a DFT calculation, it's not only EMTO, any kind of DFT calculation, we can make a little error in the density, because still our predicted total energy will be pretty accurate or very accurate. That is because it's variation. Of course, this we cannot do because we don't know the form of the functional, as you know, and then we have to split the functional into known parts, restructure the functional, and we do as usual, that you have the kinetic energy, but this kinetic energy is not the full kinetic energy, it's only for the non-interacting particles. Remember, originally the functional, energy functional, it's for interacting particles. But now we separate only the non-interacting kinetic energy. We separate the Hartree energy, the Hartree potential, Hartree energy, in fact, this, which is the electrostatic interaction between electrons. It's like charge divided by distance, that you know from high school. And that we know precisely. If you know the density, you can calculate this accurately. And then you have the Coulomb interaction with the nuclei. You have the protons in the nuclei with Z charge. Here, capital R stands for the site in your, let's say, a solid or a molecule, and small r is the position of the electron, or the position in the 3D space. Okay, so these three you can separate, and then the leftover, you call it exchange correlation. So the exchange correlation contains everything, all types of interactions which are beyond the well-known Coulombic interaction and which are beyond the non-interacting kinetic energy. And, you know, since Slater's X alpha in the 50s, there are many implementations of this, many approximations, and density function theory was considered to be a wrong and very inaccurate simplification of the quantum theory Schrödinger equation in the end. Why? Because this exchange correlation was not okay for many years. It was 87 when for the first time iron became ferromagnetic and BCC, body-centered cubic. Before that, based on this type of calculations, we couldn't get iron right. It was not me, I'm old enough, but at that time I still didn't do too many calculations. But imagine, it's not that long time ago, the end, 30-something years ago, almost 40 years ago, we couldn't describe even elemental bulk iron. But later on, there were very good approximations, and you know today that we have a pretty good control of this error, and all people who do DFT modeling know a little bit about how to handle this and which approximations can be and should be implemented. I mentioned to you that we have beyond DFT schemes, and beyond DFT scheme means, in fact, that here you do something better than a local or a semi-local approximation. Now, after having it separated, this energy, then we can do the following trick. I do a little bit faster because many of you know this, that we have the interacting, schematically, the interacting system where all electrons interact with all electrons, so they know about each other. Or you can, and then you have this red total energy, or you can replace with an effective medium or an effective potential where electrons do not interact any longer, but the potential is so that it mimics the situation from the original system. So these quasi-particles, they are not really the same particles as before, but they give the same density. So the electronic states, the end, the charge density, and then the total energy will be the same. So the total energy of this quasi-particle system is the same as the total energy of the original system. This was a very big idea, and you can make this correspondence, and then there will be an extra term in your potential, and that term comes from the electron-electron interaction. It is termed exchange correlation potential, and is the functional derivative of the exchange correlation function. And as soon as we got to this blue simplification, that is already a non-interacting system. Look at it. You have a kinetic energy for non-interacting, and density and the potential. Electrons sitting in a potential. This potential is the effective potential. It's not the true external potential. Now, if this is indeed equivalent, then we can solve it very nicely and simple. And this is what I have here. So we write then a Schrödinger equation for non-interacting electrons, not interacting anymore, independent electrons. Then the wave function, I didn't put up, but you know that in the original Schrödinger equation, the wave function depends on all electron positions or probability positions, and also the nuclei position. But here we have only one, a single. And then this can be solved. It has been solved already before the DFT was invented. So people try to use this single electron, one electron equations. That is the end, the Hartree-Fock approximations. And here you can get the solution, hopefully, and this is what I will talk about, how to get this solution. As soon as we have the one electron solution, we can construct the charge density. And remember that by construction, it's the same as the charge density of the interacting system. Then we can go back and find the potential. Potential depends on density. So this has to be solved by self-consistently, but by iteration, iterative process. So the output produces a new density, produces a new potential, and that goes back. And you repeat this until the output and the input will be the same, right? This is called self-consistent. This is why all of us who are interested and who are doing any kind of electronic structure calculation, we have to do iterations. You do VASP, you do EMTO, you do Win2K, anything. This is why you have to iterate. So the input and output, they should correspond. Now, people usually monitor something in this process, and one could monitor the density, input and output density to be the same. But as I told you, that's even if we make a little error in the density, that's not a big problem because the energy is variational. And because of that, most of DFT codes don't monitor the density, but monitor the total energy, because the total energy converges much, much faster than the charge density. Okay, so we are here. we simplified the complex problem, and the task is to solve this. You can call it Schrödinger equation or one electron Schrödinger equation or Kohn-Sham equation, because after DFT was published in 64, in 65, Kohn and Sham published this set of one electron equations. How to solve this? For an atom, you can imagine it's not that difficult task. You can do it numerically. And you have a real space grid method, and you try to solve it directly. But that's not very common. And especially for solids, this is a little bit too demanding, and then people use another way. And mathematicians know this very well, that if you have a differential equation, and this is a second order differential equation because you have a second order derivative. So the second order derivative of a wave function plus a potential times wave function should be the same as the wave function. So this is a mathematical problem. And then very often what they use a basis set of basis functions that this could be plane wave, it could be atomic orbitals, or could be something. And then you assume that the solution can be expanded in terms of these basis functions. We assume, we don't know for sure. But if the basis functions form a complete basis in your space, complete means that anything can be expanded in terms of these functions, then there is no problem, right? But usually it's complete when I goes to infinity. So you have to include many, many terms. And in practice, you truncate, of course. So completeness it's always a question in this approximation. And then what is the basis functions that decides which first principle method you use? Some methods use this, some methods those, and then completeness is a question, and how precisely you can define this basis set. And after you know the basis set, you have to find the coefficients, these coefficients, and you know the coefficients, you know the Kohn-Sham orbital, Kohn-Sham wave function, and if you know the Kohn-Sham wave function, you know the density, and you can close the loop. So it sounds pretty simple. And how to find those coefficients? Again, you go back to the variational principle. So the expectation value of the Hamiltonian, here is the Kohn-Sham Schrödinger Kohn-Sham equations Hamiltonian. You have a Lagrange multiplier because you have to keep the number of electrons fixed. N is the number of electrons. And then if this is the expansion form, and you multiply, you define the so-called Hamiltonian matrix. You also define the overlap matrix, this S. And finally, some little algebra, you find a set of linear equation and homogeneous, meaning that this side is 0. And if this side is 0, then you have non-trivial solution for C, this equation. You have non-trivial trivial solution only, and that's important, if the determinant vanishes. If the determinant doesn't vanish, then the only set of solution is that all C's are 0, and if all C's are 0, then this is 0, right? That's a trivial solution, and it's not okay for us. So we arrive to a condition that the determinant between the Hamiltonian minus energy times overlap matrix should be 0. This is very, very general, and whenever you use such an approximation, such a scheme, that you have a complete or quasi-complete basis set, then you can find the solution. And this is what is used in LMTO, in linear Muffin-Tin orbital method, for instance, and many other methods. But in EMTO, we make one more step, and that is like in KKR, you know, Koringa-Rostocker type of methods, KKR methods. And also APW to a large extent, that we don't only use a complete basis set, but we try to use some local solutions of the Kohn-Sham orbitals, of the Kohn-Sham equations. We try to use some local solution and construct the global solution, the solution for a crystal. If we talk about solving the Kohn-Sham equation for a solid, then we use local solutions as the basis set. And that's a little bit more efficient, because then you can minimize the number of orbitals. If you don't do that, the dimension of this matrix will be huge. And that is you know, those of you who are doing programming, you know that that's not the best, because it goes like n cubed. So you want to minimize this problem, and you use basis functions which are local solutions. And let me go now to EMTO and introduce you this type of local solutions. In EMTO, at least in the version that I'm talking about today, and the one that you can get from VAE, or you can get from me, or you have on the supercomputers. If you go there and you have allocation and you run calculations, you have access to EMTO. In that version, we say that the total Kohn-Sham potential, the effective potential, we approximate as overlapping Muffin-Tin potential. Muffin-Tin potential means that you have a spherical potential defined within certain sphere. The radius is S. At the sphere boundary, this potential reduces to a constant, which is called V0. So you can see that this term here in the bracket vanishes if R is larger than S. And out everywhere you have V0 everywhere. So practically you have potential which is potential wells which are spherically symmetric, but they could be large, they could overlap. I will come back to that later. And then you have a constant. This is the so-called Muffin-Tin scheme, but it is a little bit different from the old Muffin-Tin schemes that were discussed in the 70s, for instance, because their Muffin-Tin meant non-overlapping, only touching spheres. Here we have overlapping spheres. But let's, for the moment, agree that this is what we use in EMTO for efficiency. So we use overlapping Muffin-Tin potentials, and then we have to define the basis set according to that. And this plot, the figure that I have here, shows the three main parts of our basis functions. The first one, which is the red, it's called screen spherical wave, and it is a basis. It is a function, a basis function, outside of some small spheres of radius A. And by definition, these are solutions of the Kohn-Sham equation assuming a constant potential. The second one is the local free electron solution, again constant potential. That's the green, that connects the red, the screen spherical wave. It connects back to the potential sphere. Remember, potential sphere is S. This is the big sphere. We have to connect back to this point. And then we have the partial wave, which is in fact the solution of the local Schrödinger equation. It's spherical Schrödinger equation or Kohn-Sham equation, because the potential is spherically symmetric. So we have to solve for spherically symmetric potential. And this is the benefit of everything here, that we can really make it very efficient. And that's the blue. And briefly, I will talk about these three components of our basis set. So in EMTO, the basis set is composed by this blue, green, and red elements. The red goes to infinity. That connects all lattice sites. The blue is defined only around each lattice site within the S sphere, and the green around each lattice site separately, but only within the potential sphere S and the A sphere. The red component, the screen spherical wave, that's a solution of the constant potential equation. If you rewrite the Kohn-Sham equation for constant potential is V0, then it looks like this. It's a Helmholtz equation. It's called Helmholtz equation. And the solution of this is the plane wave. It's very easy. You can solve it analytically. But if you use a spherical coordinate system, then the solutions are called Bessel, Neumann, or Henkel functions. Henkel function is the linear combination of Bessel and Neumann. Bessel is regular at the origin. Neumann is irregular at the origin. And then it means that any linear combination of Bessel and Neumann is a solution, right? If Bessel is solution, Neumann is solution, then you can take any linear combination. That will also be a solution. And then we have to find a clever linear combination of these functions. And then this was the idea by Andersen in developing the EMTO theory. And this was, in fact, before the screen KKR was published. It was the first truly elegant tie-binding method in the 90s. Namely that it says that this solution should behave like a pure spherical harmonic on the A sphere with a radius of A at the origin. R is the site where an atom sits, for instance, here. So this should behave like a pure spherical harmonic on this sphere boundary, but on all other sphere boundaries, you have infinite number, remember, because we talk about FCC copper, for instance. So you have many, many, many sites. On all the others, it should vanish. So imagine you have a function that starts from this surface like a spherical harmonic and then goes somehow, and then it goes to zero here. But it goes to zero here. If you have another site here, it should go to zero there. And because you force this linear combination to go to zero on all other sides, it will have a short range, meaning that in real space, with the distance, it will decrease, and vanish finally. And this is what it is called screen spherical waves. Mathematically, you can write in this form. So you have a pure YLM term, pure spherical harmonic, something times a spherical harmonic, that's called pure YLM term. And then you have a linear combination of YLMs on all the other sides. You see R prime. On all other sides, you have a linear combination. And that means that the screen spherical wave, the end, cannot be written as a pure YLM. The coefficients here, you see two functions, F and G. I will define in the next page. The coefficients here, which is kind of expansion coefficient, because the screen spherical wave around side R, and here around side R prime, another side, or R double prime, something in the space. Then it's like a two-center expansion, and these coefficients are called structure constants or slope matrices. And those of you who are familiar with EMTO, you know that there is a program block that calculates exactly these matrices. They are very, very important because that gives information about where all the other atoms sit. Okay? Now we go to the, I want to introduce you this F and G. So I put up here the same formula, and then remember the boundary condition was that the screen spherical wave should behave like a pure spherical harmonic on its own sphere, meaning that when R is A, so we are at the original sphere surface, then F should be 1 and G should be 0, because this term should vanish, and then we have a pure YLM. And that means that the functions should fulfill this boundary condition. And then there is another boundary condition for the slope, that it should vanish, has vanishing slope on A, and the slope on the second term should have a slope of 1 over R sphere. That's a definition. It could be 1 over A square or whatever. That's only one choice. There are many different choices, but the implementation you can reach today uses this scheme. Now, easily you can put this boundary condition and say that, okay, this is a linear combination of Neumann and Bessel functions. Then there are some expansions, then some coefficients here, and joined with this boundary condition, you can arrive to the condition that these T coefficients, T1, T2, T3, T4, should look like this. They are numbers, complex numbers, and it's called screening matrix. So if you decide about this screening, how to localize these states, I will tell you why you need to localize it. Then you know the screening matrix, you can construct this F and G. If you know F and G, you can construct the screen spherical wave. That's all. Okay, so we are done with the red part. Now we go to the green part, which is a local free electron solution. Again, is a free electron solution. Free electron solution means that it's a solution of this equation. But it's a local. It's defined only between the two spheres. So then it has a pure YLM character. It's a radial part times YLM times a spherical harmonic, and it looks like this. It turns out that it has a very simple form, the same F function as before, the same G function as before, and there is a coefficient here. We construct this. If you use the same, it turns out that on the A sphere, this has the same value as the screen spherical wave. So indeed, the green and the red, they meet here. They have the same value, but they do not have the same slope. There is an angle here in between the two. They don't join smoothly. And because of that, originally they were called kinged partial waves, because there is a kink here. And then on this sphere, on the S sphere, on the potential sphere, it joins smoothly the blue solution. And this joining smoothly, that means that value is the same and the slope is the same. And from this, you will be able to find the D matrix, the D coefficient from this condition. I tell you immediately. So we come to the blue, the partial wave. That's a solution of the radial Schrödinger equation. There are many standard solvers. If you know the potential, you plug in the potential, spherical potential, it gives you the solution, the regular solution. This blue is the regular solution. They are like the 1s, 2s, 2p, 2d, 3d, and so on, orbitals, atomic orbitals, similar to those. Not exactly atomic, because its potential is not atomic potential, but it's similar. So you can find this blue, okay, regular solution, that gives a Schrödinger solver or Dirac solver, provides this. And then as soon as you know the blue, you know the value and the slope here, then you ask that this green should join this in value and slope. Then you get this smoothly, then you find the end the D matrix from this condition, as I told you. So then, as soon as you know, you can go back with blue here and continue with that. So we have the three components of the basis functions. And remember, by construction, the blue is a solution of our Schrödinger equation. So it is different from the variational principle because here we don't use an ad hoc basis set, but we use a clever basis set. It's not specific to EMTO, it's specific to all KKR type of methods, that we use a clever basis set that is locally is solution to the Schrödinger equation. And then what we have to ask for is that, of course, the red goes and connects all lattice sides, so that's okay, we are happy with that. And then it will be a solution for the whole crystal, but there is a little problem, and that little problem is this kink, this slope difference here. Because the end, the Kohn-Sham orbital, the wave function should be smooth and only the value and the first order derivative. You know this from quantum mechanics. So we have to kill this kink somehow. And this is what EMTO does. So you have the EMTO orbitals. This is the basis set. The screen spherical wave, the partial wave, the local free electron solution. They are the three: screen spherical wave, partial wave. This is the red, blue, and the green components. This is the basis set. Remember, I told you that you have to have a good basis, but now we take this as a basis. Then we put into this expansion. We expand the Kohn-Sham wave function in terms of these basis functions. So we take this psi bar times coefficient. Here the coefficients are called V. So V times psi bar summed over all orbitals. And explicitly, after you substitute this form, you will get one term, V times this. You see here V times the partial wave. And you have V times this free electron solution that is here, down here, is exactly this bracket is the free electron solution times V. Of course, you have the Y because you have the 3D. And then you have the Y times, in the bracket, the screen spherical wave. So what I introduced, this is the blue, this is the red, and this is the green components. By construction, remember, this was a solution to the Schrödinger equation in the sphere. This is not a solution of the Schrödinger equation in the sphere, because within the sphere, potential sphere, the potential is not constant. It's spherically symmetric, but not constant. So these two terms here, they are not solution. This is solution. So what we have to ask for is that these two should cancel each other, right? That is a condition. And since there was a slope difference, then or kink, then we call it kink cancellation. Why? Because the kink should be cancelled. So the linear combination has to be made so that that extra kink that is present should disappear. The F drops out. From here, this plus and minus. You remember here it was a minus. So they drop out, and then it will be G times this term S minus D. If you rewrite, you find something that sum over all RL. A is, we introduce here to make it hermetic, the matrix, otherwise you could drop. Then you have S, the slope matrix, minus this D, which is the, you remember in the previously I told you that from the matching condition you find it is called logarithmic derivative. And that is a set of linear equation again, homogeneous. And we have to find the V's. We find the V's if we say that the determinant of this equation should vanish. So we have to ask that the determinant of this equation vanishes. And that is the kink cancellation condition, kink cancellation equation. Finding the zeros of this determinant is the task, we have to do. It could be done directly, but remember, this depends on energy, this depends on energy, and these energy dependencies are not simple. So finding the zeros is not easy. So because of that, already in the first implementation I used Green's function method, which practically means that you don't find the zeros of this determinant, but you find the poles of a Green's function defined as the inverse of the determinant. You know, where the determinant vanishes, there the inverse of determinant diverges. So you have to find the poles, the poles where it goes to infinity. And that is what we do in EMTO. Practically, remember, S is the expansion coefficient, gives the structural information, and D is the matching condition between the green and the blue parts, and it is an information about the local potential, the potential. So this gives the chemistry, and this gives the structure, right? It's so simple. After you find the determinant where is zero, you find the so-called those energies where you have this matching this condition fulfilled. Those energies will be the Kohn-Sham energies, one electron energies. Those energies will be the energies where you have a solution, right? And then you put those energies back and you find the coefficients. You find n-1 coefficient, of course, because the determinant is zero, then the size of the set of equation goes down by 1, but the last one you find from the normalization condition, so everything looks fine. We could solve the Schrödinger equation in this elegant way. And look that the size of this equation is not that big. You have L, the capital L stands for orbital and magnetic quantum number. If you include in your basis set S, P, D, F orbitals, that means 16 channels, in fact, 16 by 16. And then R will be the atoms, how many atoms you have in the unit cell. That could grow, but still it's solvable. And the normalization condition always needs the overlap matrix. Normalization means that you take the square or the product between complex conjugate and the original and integrate in the whole space, and it turns out that that's nothing else than the energy derivative of this matrix. So when you know the slope matrix and the D, and you know their energy derivatives, you know the overlap matrix. If you know the overlap matrix, you can normalize your states. And this is why EMTO is called EMTO, because we can get this, and we can properly normalize our states. Even though we do a Muffin-Tin approximation, but the states will be properly normalized in real space. And that is very, very important. Without this, we would not be able to do precise total energy calculation. You should remember. So the K dot here, D dot, S dot, that's energy derivative. And this is why in EMTO we compute the slope matrix, but we also compute the first order derivative, energy derivative. Okay, now that's the two main components, slope matrix and logarithmic derivative. And I will talk about the slope matrix a little bit in the next. Then I talk about the potential, and then we turn to the energy, total energy. Slope matrix that we compute in one program block called KSTR. Maybe we will talk about that later. And analytically, it is this form. The T matrices we introduced, they are the screen matrix elements. D is also known from the T matrix elements, this little d. And S0 is nothing else than the expansion coefficient of a Neumann function centered on site R in terms of Bessel functions around site R prime. Two-center expansion. If you open a mathematical book, you find this expansion. In one-dimensional, it's called, I think it's two-center expansion. This is three-dimensional. So the slope, the coefficient here analytically is known. We can compute. You plug that in here. You take this inverse of this matrix, and you find the S of A. A stands for the fact that we define this in connection with a certain set of hard spheres, small spheres. I will show you the effect. And on these two figures, you see how this S behaves in terms of energy. Here, the energy is omega, but omega is, in fact, energy minus V0. In fact, times Wigner-Seitz radius square. I tell you later. It's a dimensionless quantity. But it is relative to V0. So remember, it's relative to V0, meaning that the average constant, relative to the average constant potential. So 0 is in fact the average constant potential at the 0 level. And then you see this is the real energy, this is the real component of the energy, this is the imaginary component of the energy, and then you see the real part of S and the imaginary part of S. What you can observe immediately that it's a smooth function of energy. It looks nice. This was for FCC lattice. It's a smooth function of energy. It has both complex and imaginary and real components, especially for energies around 0 up to +5 in these units. It looks very nice. It becomes red. It becomes ill-behaved a little bit higher and positive energies, but otherwise it's very elegant. And that it was in 98 when we realized this, and then we said, oh, but then why don't we use a kind of expansion for it? And I come to that immediately. Before that, let me show you, because I told you that the slope matrix we compute for a set of A spheres. But what happens if you change the A spheres? And on this figure, you see the slope matrix for different shells. You know, in a crystal, you organize the atoms in different shells, at different distances from the origin. And the numbers here, you see it's the distance. This is the on-site term. This is the first coordination. This is the second coordination. This is for BCC lattice. You can recognize that in BCC you have square root of 3 by 2. That's the shortest distance to the nearest neighbor. I mean, it's the nearest neighbor. This is the second nearest neighbor, third, and so on. The shells in a crystal. And then you see that there is a factor of 10, 100, 1,000, 10,000. And meaning that they decrease, which is very good. But we don't only want to decrease them to decrease as a function of distance, but we want them to vanish. And then we talk about screened formalism, tie-binding formalism. This is what it's meant by tie-binding formalism. And look at it, there is a range of A spheres around 0.6 in terms of average Wigner-Seitz radius, where they vanish. This already, it's very small, and these are not big. But at high distance, they indeed vanish. And you can calculate at even higher distances, they disappear. And that is what makes tie-binding. And why we want it to be tie-binding? Because if it's tie-binding, then the size of this matrix, it's finite. You can do this calculation in real space. Most of you are young, you don't know. In the 70s and 80s, people could not do such calculation in real space. Why? Because on this figure, you see it's large even at high distances. And then they had to do, employ the Ewald technique and calculate these slope matrices in K-space. And that is not very efficient. But having tie binding, you can calculate in real space. And that's a really great benefit for EMTO, that we can do that in real space. For instance, you want a K-point, a Brillouin zone convergency test. In the old days, when you increase the number of K-points, you had to recalculate the slope matrix. But now, you don't need to do that. You calculate only once. Those familiar with EMTO, you know, in KSTR, we do this calculation, and then you can increase the number of K-points using the same slope matrix. That was not possible 20 or 30 years ago. So that is why we want a screen formats. This has nothing to do with Muffin-Tin approximation. It is only the way how we compute and take into account the other lattice sides in a crystal. So remember 0.6, and this is why you find in KSTR input file that the hard spheres are 0.6, 0.7. And then you need to use 80, 90 lattice sides to get very good description of the crystal structure. Coming back to the energy dependency, I told you that it's relatively smooth function, this slope matrix, as a function of energy. Then we can use a kind of Taylor expansion, right? You know Taylor expansion. This is a Taylor expansion. So zeroth order term, first order, second order, and nth order term. And on this figure, you see how they behave. The relative error compared to the exact value using a third order Taylor expansion. And you see, here it's very precise. The expansion is around 0. It's very precise. But as you go further, the error increases. It's 50% error. That's huge. So it's not okay. But then if we go to the 6th order expansion, it is much, much better. So you have a big window here. 5 is pretty large, plus minus 5. Look at it. It's in terms of kW square. Omega is kW. K square is energy minus V0. So if you have one Rydberg energy window and W is square is like 5, and there you have very good accuracy. And this is the accuracy for the energy derivative. Remember, we need also the energy derivative, not only the S, but also the energy derivative of S. And we have good accuracy here. And this is the standard setting. If you do EMTO calculation, most of the time you do a 6th order Taylor expansion for the slope matrix in terms of energy in the complex plane. And it works fine. But sometimes it's not good enough. And then what we did about 15 years ago, we said that, okay, we should modify it and don't use a Taylor expansion, standard Taylor expansion, but we should use a two-center expansion. It's like expanding a function around 2 points in the space. So you know the value of the function in 2 points, the first, second, third, and so on, derivatives in these 2 points, and do the expansion. Mathematically, sometimes it's termed as Hermit expansion. It's a two-center Taylor expansion. And then you see that the error drops, and we can go to plus 10, minus 10 window, also for the energy derivative. We get very, very good accuracy. And this is very important because sometimes you have to treat systems with semi-core states, meaning that not only the valence states you have to describe self-consistently, but also the deeper lying electronic states. Like take an early transition metal or take a light actinide, then you have to do that. And then you need much higher accuracy within a big energy window. because we have to count, the kink cancellation equation. We find the poles. We take the inverse of the kink matrix and find the poles. And finding the poles we do by the residue theorem. If you are familiar in complex analysis, residue theorem says that if you integrate a complex function on a closed loop, then you find the number of poles inside that loop. So practically we do that. And finding the number of poles on the real axis, we have poles on the real axis, we integrate in the complex plane. And we need to include in that complex plane the semi-closed states as well. And then we need such accuracy. This is implemented. You can do this modified two-center expansion in EMTO, and it gives very good results. The CPU time doesn't increase significantly. Almost. They can tell how much, but very little. Good. Then you may ask, okay, but how I control the accuracy? Do I get a good result? And in my book, you can read about it. The slope matrix and the energy derivative of the slope matrix gives the overlap matrix. You remember? Overlap matrix normalizes the electronic states, the Kohn-Sham orbital. So we have to be very, very accurate on the slope matrix level. But we have to be very accurate also in the real space integration, how we integrate in the real space. I will tell you immediately how we do that. And then after you do the self-consistent calculation, you can count how many states you have indeed in your unit cell. If the slope matrix was calculated very precisely, you will find the right number of electrons. And you see here, this is copper, FCC copper. And indeed, you find the right number of electrons if you converge your real space integration very nicely. And also the L truncation for the charge density. Remember the charge density, it's expanded also in terms of spherical harmonics. And this L-MOX is the expansion cutoff for that. And it goes very, very close to you notice the scale. This is 0.02 electrons. So we are very, very accurate up here. So it's good, but it's a very strict condition to verify the accuracy of your slope matrix and the real space integration. And whenever you do a new system, I advise you that you have a look always to the charge misfit. It should be very, very accurate. I come back to the potential very briefly. I told you that we use Muffin-Tin potential, optimized overlapping Muffin-Tin potential, that I defined this form to you. On this figure here, I tell you the error in the potential for a model potential, not for a real potential. I only took a cosine potential. It's a model. Cosine potential, that's exact potential, and then I use this Muffin-Tin approximation and look at it. If you do this and increase the sphere size radius, your error goes down. And that explains why we do overlapping Muffin-Tin potential. The error could be 10% at touching sphere, but if you let the potential spheres overlap, it goes below 5%. So you can practically map your total potential, the real potential, by spherical potentials, but they must overlap. And that is why it's called optimized overlapping Muffin-Tin potential. A very important parameter is the Muffin-Tin discontinuity, how much the potential jumps at the sphere boundary. That also goes close to zero if they overlap. So we are very good. And although I didn't emphasize too much, but the screening and how the slope matrix behaves, that depends on the level of V0. If V0 goes closer to zero, you have a better screening, and that also happens, you see? it comes closer to 0. So all these critical parameters improve a lot when you let the potential spheres overlap. And that's why we adopt this overlapping Muffin-Tin sphere. Those of you who are familiar with the old electronic structure methods, you heard about ASA, atomic sphere approximation, but this is not ASA, this is beyond ASA. Okay, this is an example how the potential optimization works, iron-carbon system. You take this is the total energy, and you see if you change, this is C over A, iron-carbon is the martensitic steel, building block of martensitic steels. And then here you change the potential sphere, and you see that you can minimize the energy and find the value around 0.75 for carbon, where you find very good lowest energy. And if you use that, then the VASP and EMTO results, even for this very complex system, because it's a distorted body-centered cubic lattice, it's a body-centered tetragonal, in fact, with interstitial carbon. And you get good agreement between VASP and EMTO. Remember, VASP is full potential, pseudo-potential, but full potential. EMTO is not, but still we get, due to the fact that we use optimized overlapping Muffin-Tin, we get very good accuracy at a lower price. That's good, but then why do we want, if they are the same, VASP and EMTO, then why do we want EMTO at all? And about 22 years ago, I combined EMTO with CPA. At that time, I worked with Igor Abrikosov. Igor is now professor in Linköping. Many of you know him. He was at Uppsala, and we discussed, and he was expert in CPA. So I implemented CPA in EMTO. CPA means that you have a solid solution, a random solid solution, that you replace by an effective medium. Effective medium means that everything is the same, but we don't know what is everything, but I mean, what is the same, what is what we call the same, but then we put the A to A1, A to A3 impurities one by one into this effective medium, and then we say that the average of these impurities should give the original effective medium. Mathematically, it looks like this. You solve the kink cancellation equation now, but you solve for the effective medium. So this D is not a real potential. It's not a logarithmic derivative of the real atomic potential, but it's the logarithmic derivative of the effective medium. After you find the solution for that, in fact, the Green's function for the effective medium, then you solve the Dyson equation. It's an impurity problem. When you replace the effective medium potential, the tilde, with the real potential, the impurity potential. Those of you who are familiar in Green's function formalisms, you understand. If you don't, I can explain more. So this Dyson equation you solve for each impurity, that is solving separately this, that. And then after you find the impurity Green's functions, the configuration average of the impurity Green's functions should give you the effective medium. And then you again have a self-consistent question. You have to solve it self-consistently. So you have one self-consistency for DFT and one for CPA. And the true benefit of EMTO is that we can do that, and we can still keep the accuracy relatively high, almost at VASP level, but we can treat random solid solution. Okay. The methodology part now, I finished the self-consistent part. I would like to talk a little bit about the total energy. Then I have a lot of examples that I was going to show you, but it's 11:30, and I know that I should finish around 12 or even before. I go on with the total energy, because those of you who would like to use or are using EMTO, you should know how we compute the total energy. And then if I have time, I will show you a few examples. So we go back. This is the Kohn-Sham equation. You remember we defined at the beginning, it's a single electron equation, one electron equation. And the EMTO gives a way of solving this equation. As an output, we get the charge density. Then we have to put this into the total energy and try to calculate the energy. It contains the kinetic energy, it contains electrostatic energy. Now, in the case of a solid, it's not limited to a solid, crystalline solid, but I will explain you how it works for a solid. For a solid, the electrostatic interaction between atoms, this Hartree, it's called Hartree term, you split into two. One is interaction with electrons within a cell at the origin, and interaction with all the other electrons which are outside. And which are within the cell, you call it intracell contribution, and which are outside, you call it intercell contribution. It's just a matter of, because you see here, you have to integrate over the whole space. And this integral domain, you split into two. One that is the cell at R, and then the rest. Then, of course, you have the exchange correlation that also, since we use local or semi-local approximation, it is there at the site I, or R. And then here you see a small index I, which is for alloy, and you have a C, the concentration of the alloy components. So if you have a two binary alloy, then I can be 1 and 2, and it's the concentration of component 1 and component 2. The intracell you calculate separately, intracell Coulombic energy, and also the exchange correlation. The intercell you have to calculate within a mean field, because if you have a CPA, you know the impurity, but what is beyond the impurity you don't know, because it's CPA is a coherent potential approximation. It's a single site. So you have one single impurity embedded in an effective medium. So what is outside, you have to treat this as an average. So this is why you don't have an I here. And then there's a little correction term, which is called screened impurity correction. And it is connected to the single site approximation. Okay? Let's take now, before we do that, this integration we have to perform somehow. And all of you know how to integrate, but when we have a three-dimensional problem, like the Brillouin zone integration, in the Brillouin zone we use special points, or we use uniform K-mesh, and that's a polyhedron. And integrating in a polyhedron is not that easy numerically, but when you have such like charge density and so on, you need much higher accuracy. And then people invented many different techniques. What EMTO uses is the so-called shape function technique. And let me spend 2 minutes with this. It's pretty trivial quantity, but at least you know why we have a program block called shape. Shape function is a step function. It is one within the polyhedron. Polyhedron is the Wigner-Seitz cell, for instance, or Voronoi cell around each atomic site. So you divide the space into units. Space filling, some polyhedra, set of polyhedra. Because you have to integrate in the whole space, you have to divide. The shape function around site R is defined as 1 if the position is inside the polyhedra, and 0 otherwise. It's a step function. And then we say that, okay, step function, but we expand in terms of spherical harmonics. So we expand. This is an expansion. It's a standard expansion in terms of spherical harmonics. Y is spherical harmonic, A sigma R is a radial solution of the shape function. We can easily invert this expansion and calculate these coefficients. And in the shape, so-called shape program block, this is what we do. And on the figure, you see some components of the shape function for an FCC lattice, if I remember correctly. Yes. And you see this 0, 0, that's L equals 0, the orbital and magnetic quantum numbers, or 4, 0, all the other components vanish. They are not shown here. There's no P and D components, and F. 4, 0, like that, and 4, 4, and so on. You see these shape functions. They can be calculated partly analytically, partly numerically. So inverting this expansion, you can do the calculation. And now what I want to show you that if we have the shape function and you have to carry out such an integration, so you have a density times some kind of kernel of the integral, and you have to integrate within the omega, the Wigner-Seitz cell, then you say that, okay, I integrate within a sphere which contains my cell. Usually we call it circumscribed sphere, but it could be larger. And I put here the sigma. The rest is the same. By putting here the sigma, sigma kills everything which is outside of omega, because it's a step function, right? So it's easy. But then my integration is not on a polyhedron anymore, but on a sphere. And that is what makes nice. Because here I have sigma times n. Look at it. Sigma times n, I can write as an expansion. Why? Because sigma is expanded in terms of y, spherical harmonics. N is also expanded in terms of spherical harmonic. So the product can also be expanded. You know these Gauss coefficients. Probably you heard about Clebsch-Gordon and Gauss numbers. This n tilde can be written in terms of those. In fact, the components of sigma, the components of n, and then you get n tilde. That's very well defined. And in KFCD part of the EMTO, we compute this n tilde. As soon as you know n tilde is the component of the charge density when the shape of the cell is taken into account. Then you can easily rewrite this integral into a one-dimensional integral. So a three-dimensional integral, it's written as a one-dimensional integral. And numerically, that's a very big step. Not only that you save CPU time, but also it is much more accurate and much more stable. But here you don't have n, but you have n tilde that contains the shape of the cell. And this is what the shape function solves. So that is why we need to do the shape function to take into account the proper cell size, cell shape. Okay, let's go back to the total energy. So remember, we always use shape function for all integrals. The kinetic energy, kinetic part of the total energy, I highlight here by red, that we calculate in the standard way as all electronic structure methods do. That the functional you don't know, no one can give a good kinetic energy functional today. There are groups of people working in the world trying to develop, establish better and better kinetic energy functionals, but so far we don't have a general universe. For special cases we have, but not universe. Because of that, the kinetic energy we calculate by definition. The kinetic energy is nabla squared times applied to the wave function, complex conjugate. This is the definition of the kinetic energy, non-interacting kinetic energy. We have to sum over all occupied states. If you use the Kohn-Sham equation itself, you can express this quantity like one electron energy. Remember, the one electron energies we get as the zeros of the King equation determinant. So we know this, we can get that. And then there is a double counting term, potential times density. So the kinetic energy, it's 1 electron energy minus NV. It's also like in EMTO, like in other methods. And that is why we often talk about the 1 electron energies, because it's a very important part of the total energy. So the total energy of the system starts with this sum of the 1 electron energies. All the other terms are functionals of the density. Okay? It's also called band energy. Then the intracell. The intracell is the electrostatic interaction inside the cell. So you have one cell, 1 omega. That is a normal Coulomb interaction. But now we have to have the N tilde because we have to take into account the shape of the cell. This is pretty standard form. The details you can find in my book, but in many other books as well. There is a P and the Q functions. N is the density, and P and the Q functions are defined here. Everything is in terms of N tilde, components of N tilde. If you know N tilde, you can calculate P and Q, and then you can calculate the intracell energy. And it converges very nicely. There is no problem with this term whatsoever. The intercell part, on the other hand, often we call it medal. And that is the interaction between this side and another side, this polyhedron, electrons within the polyhedron at R, and electrons within a polyhedron unit cell at R prime. And this Coulombic interaction, after some mathematics, can be written in this standard form. There is a Q, another Q. They are called multiple moments. It is defined here. The multiple moments have to be calculated for impurities. So there's an I here, you see, meaning that we have alloy component. But the end in the intracell energy enters the configuration average of the multiple moments. This M matrix is the Madelung matrix that we calculate in the BMDL block of EMTO. That is why we have the BMDL separately that calculate this M matrix. This expansion is very good. The Qs you can see here, the multiple moments for some surfaces. FCC1 surfaces, you see the multiple moments can be quite big, and how they change as you go across the 4D metals, including the simple metals. And this form is perfectly fine for those cells which are far away from each other. For those cells which are close to each other, this form doesn't converge. You see here we have L summation, and how far you need to go with L. In principle, you go to infinity, but in practice, of course, you truncate somewhere. And the expansion for neighboring cells, this expansion diverges. And that is a problem, a standard problem in electronic structure methods, especially KKR and related methods like EMTO, that you have to treat this problem. I will not talk about that here. You can find in my book and some of our publications, it's called near field correction, and those cells have to be treated separately. Otherwise, you don't get a good total energy. And then you have the exchange correlation part that since exchange correlation depends, it's a functional of the charge density. You cannot simply use the shape function, because the shape function could be combined with this n, but inside it's, and then this exchange correlation energy density, you have to expand in terms of spherical harmonics. And that's not very easy, because this itself depends on the position, on the angular and radial coordinates. And because of that, we don't use the shape function here, but we use a direct space integration, three-dimensional mesh, it turns out that if you are careful with the truncation for the shape function, the shape of the cell, and you are careful with the mesh for the surface, theta and phi, you know, the angular coordinates, then you can control this error. And what you find implemented and in the input files in EMTO, it's well converging behavior. You see, if you use a few mesh points, then it's even diverging, not converging. But if you use a high density mesh point, it behaves nicely. And that's connected with the fact that the shape function itself for very high L has more structure, more changes the sign more and more times. And therefore you need a high density of theta and phi mesh to capture that. But that's pretty, it can be controlled pretty nicely. So the default is in the input files, and if you change, that's okay, but you should remember that it can bring 16 milli or 8 millirudberg is a big energy, very big energy. You wouldn't be able to get anything very precise if you don't control this. Okay, I give you a very, very few results. When you have an electronic structure method, the first question, very first question you should always ask. In fact, if you start a project, any project, the first question is, do I get a good equation of state? Do I describe properly my niobium, for instance? If you don't describe correctly the equilibrium volume, why do you expect to be able to describe any very fancy physical property? So always ask that question when you do electronic structure study, modeling. So what I did on the first figure, you see equilibrium volumes for many metals. On the horizontal axis, you have full potential, like VASP or full potential LMTO or Bin2K data. And here you have EMTO data. And you see the agreement it's good. It's very, of course, the employed exchange correlation has to be the same. Otherwise, you don't get such a good agreement. But if you are careful about that, you get. This is the equilibrium volume is the minimum of the binding energy, right? Of the total energy. You have the total energy like that. This is the equilibrium volume. The curvature of this energy versus volume, it's the bulk modulus. It's this one, the curvature. So it's not only the minimum position, but also the curvature has to be described properly. And that's called bulk modulus. That's the second order derivative of the energy. This is energy versus volume curve. It's the second order derivative, gives the bulk modulus. On this figure, you see that. And again, you find that the agreement is very good. It's much more tricky quantity because it is not the minimum, which is a robust quantity, but it's the curvature. And remember, this is a quantity that tells you how stiff your crystal will be against changing. The hydrostatic pressure, how it will affect your volume, in fact. But also it's connected to the phonons, the end, the thermal properties. Smaller the bulk modulus, bigger effect the temperature will be on your system. So it's important to know this, and you'll find it. Then you also have some hexagonal lattices, for instance, where it's not only the volume and the bulk modulus, but there is also another structural degree of freedom, and that's the C-axis relative to the A-axis. On the third figure, you see the C over A for all hexagonal metals. The agreement is not very bad. You notice the scale. I would say that it's very good, and some cases it's even better than full potential. And those cases where we don't have that good agreement, there we have an explanation. Why? For instance, yttrium in full potential, it was very, very bad. It's outside of the figure. But in general, it's a good agreement. Okay. Surfaces. You would expect that when you do such Muffin-Tin scheme, you cannot describe very non-homogeneous systems, but it's not true. This is the surface stress. You know, surfaces are described by two main physical parameters: surface energy, excess energy. So you cut a crystal, you make a surface, and that costs energy. And then also you stretch. You can stretch the surface, and that's called surface stress. And that's like a force. And on this figure, you see the surface stress for HCP, BCC, HCP, and FCC crystals for 4D metals. And the agreement between VASP and the EMTO, it's reasonably good for such delicate question.
Just a workshop.
Okay. Then I have a large set of demonstrations for alloys, but I give you only a few at the beginning. These were very old studies, and you know, now it's pretty standard. And thanks primarily to EMTO. Even after 20 years, people, when they do such calculation, they use EMTO because it gives good elastic constants, not only for pure elements like aluminium here, but also for solid solutions. And you see the solid line is the calculated EMTO values for assuming random solid solution, and the symbols are experimental data. And the agreement is not bad. Aluminium, lithium, aluminium, magnesium. And we have many other cases. And here I would like to tell you that in order to get such good trend, you see the absolute value is a little bit shifted, but the trend is pretty good. And that's important. The absolute value is shifted because even the DFT approximation, the exchange correlation approximation, affects the absolute value. You get such shift in VASP and other tools as well. But the trend is well captured. And you get smooth, nice effects, alloying effects. But numerically, this is quite demanding study, because you will see, if you try to do such, you will see that how you map the brilliance zone, how you integrate in the brilliance zone, it's critical to be able to get good trends. But it is possible to control the data, especially in dilute alloys, low concentration alloys. It's a important question. This was silver, zinc. Silver and zinc, they form FCC solid solution in silver-rich part, and BCC solid solution around echiatomic composition. This is FCC, and this is BCC. And the calculation, the solid line, is for hypothetical FCC or BCC everywhere. And we have some experimental data as well. Again, the slopes are very nice. The absolute values are not perfect, but the slopes are very nice. And up here, on the zinc-rich part, it should not be neither FCC nor BCC, but it should be hexagonal. And here I show you the hexagonal silver, silver zinc. In silver part, if you could stabilize hexagonal, it would have an almost ideal silver A. Ideal silver A in hexagonal is 1.633. But as you add more zinc, it goes below the ideal one. Pretty much below. And then in zinc-rich part, where you have almost purity, it goes high. You know, zinc is a hexagonal metal with very high silver A. 1.8 something, unusually high. And this trend is very nicely captured by ab-initio calculation. You get pretty accurately. These are old calculations. They are like 20 years old calculations. But even today, you can get this behavior. On this figure, it's a map showing for the same system how volume and composition affects the C over A. You see, when you have high volume, your C over A is here, but both volume and composition affects the equilibrium C over A ratio in your alloy. As a last example, let me talk about iron. You know, iron at low temperature is ferromagnetic and BCC, body-centered cubic. But around TC, it goes from body-centered cubic to body-centered cubic, but paramagnetic, right? So, you know, if you look at the iron phase diagram, in iron, you have a magnetic transition around 1040 Kelvin, where it goes from ferromagnetic to paramagnetic, but keeps the same crystal structure. And then people always asked how to describe this paramagnetic BCC. And also then it goes to FCC, a little bit higher temperature, and then back to BCC, epsilon phase. So alpha iron is BCC, gamma iron is FCC, and delta iron, probably delta iron is BCC again. And then people, you see here two attempts to describe. And look at it. Here at TC, you find negative curvature. This is C over A, and this is energy. So here, BCC iron is, paramagnetic BCC iron is mechanically unstable. Here, look at it. In ferromagnetic state, iron is stable, but in paramagnetic state, which we model by DLM, it has a negative curvature. It's mechanically unstable. When the energy has a negative curvature, it's a maximum, then it's not stable state. It's not even metastable state. And we did this calculation with the EMTO. You need CPA here because you want to describe the paramagnetism. So here the alloy theory is employed in order to describe the magnetic randomness by the so-called disordered local magnetic moment picture. And you see, you have the body-centered cubic paramagnetic, which did with this volume and this local magnetic moment. And you have the face-centered cubic, which has a smaller volume, and this magnetic moment. Both of them are magnetic. And I want to show you this figure, that this is the so-called Bain paths connecting the BCC and the FCC. The BCC is at 1, C over A1 is BCC, and C over A square root of 2, 1.41, that's FCC. And this figure here is for non-magnetic iron. Here you see the density of states for non-magnetic iron. So they correspond like this to each other. And non-magnetic iron, FCC is very stable compared to BCC. The energy is much deeper here than there. And here it is a maximum, local maximum in BCC. And that's connected with the fact that in body-centered cubic iron, non-magnetic has a large density of states at the Fermi level, making this alloy unstable. If you don't open for magnetic polarization, magnetism like itinerant magnetic splitting for iron, you have very unstable, and that's seen here very nicely, and FCC is stable. But if you do paramagnetic state, the density of states loses this peak, in none of the C over A, these small numbers show the C over A. It's small density of states, smooth around the Fermi level. And you see that the iron has two states. One is BCC and one is FCC, right? So paramagnetic iron has FCC and BCC energies very close to each other. And both of them are stable or metastable. It's very important. The energies are very close to each other. This energy minima is what you see here, realized at slightly different volumes. BCC has larger volume, FCC has smaller volume. Exactly, FCC has smaller volume, BCC larger volume. But both of them are mechanically stable, meaning that you can, if you use EMTO, you will be able to describe paramagnetic iron. And if you describe paramagnetic iron, you can describe paramagnetic iron alloys. And you can describe paramagnetic iron alloys in FCC and in BCC. And we did that. And that's, here I stop. This is, for instance, an FCC paramagnetic iron alloy. You see the elastic constants calculated by EMTO for this iron chromium nickel alloy in the FCCs, and it's paramagnetic and FCC, and the errors in C11, C12, C44, pretty small. This was like 20 years ago, this, and then later on we, thanks to this, we also started calculating other properties like stacking fault energy. Stacking fault energy as a function of nickel content or as a function of temperature or for specific alloys. And turned out that indeed, when you combine with alloy theory, you get very good feature. Now, I still have many slides, but it's noon, so I will stop now. But let me come to the last slide. So the kind of take-home message that EMTO we could combine with alloy theory. The alloy theory was blamed for many years that it's not precise, this mean field alloy theory. But the main problem with that was that it was combined with other solvers which were not good enough. We were lucky when we did this marriage, and it turns out that it can capture for chemical and magnetic randomness the trends very nicely. Then you don't have a closed spec system, you pay attention to the Muffin-Tin. It's very important because overlapping Muffin-Tin, optimized overlapping Muffin-Tin should be handled properly. We have screened, localized feature. We have smooth energy dependency for the slope matrix, making it possible to expand in terms of energy. The potential is optimized. We can optimize. We have right normalization, thanks to the fact that how the theory is formulated. And then the energy we calculate from the full charge density, and that makes our energy pretty accurate, making the kinetic and the total energy quite accurate. So in summary, I advise you that if you have such a question, to model an alloy-related problem, try to do that. Very often we combine EMTO with VASP in the sense that we do a structural optimization by VASP for a certain composition, for instance, and then we go further by EMTO, like grain boundaries, you know, grain boundary in a polycrystal that needs a very careful structural optimization, and we do that with VASP. After we find the proper geometry, atomic positions, then we do alloying with EMTO. Within certain limits, it seems to work pretty nicely. It's a good combination. Surfaces we combine, and many other cases. Sometimes when you have an alloy, a binary alloy, or multi-component alloy, you might have large local lattice distortions around the alloy components. Those cannot be captured by CPA. They are not part of the CPA, but you can do it with VASP. And then you can combine, you can calculate this lattice strain, lattice distortion contribution, and add to your EMTO CPA energy. Okay, I think with this I stop. And I took a lot of time, but you will continue in the afternoon, I guess.
Hello, everyone. Welcome back to our EMTO training workshop. This afternoon, I will stay here with you for some hands-on access with EMTO code. So I will start with this quick setup for this workshop. For training, we use two supercomputer resources. One is from Tetris in NAISS. One is Leonardo Booster from Italy. And all the users from Sweden who can access Tetris was be added to a project. And Leonardo Booster, these two supercomputer setup may be a difference. When you go through this training material, you can always click these tapes for different commands.
Maybe we can give the participants several minutes for them to log into the cluster.
Yeah, maybe I leave 1 or 5 minutes for
yes.
everyone to log in to the computer. If you don't remember, please check the email. I think you only send all the participants about this temporary user log into the Leonardo. For the Tetris, I believe everyone has a account on Tetris could log into it easily. Now for the Leonardo Booster, everything was set up in this modular. Before you load this modular, you need to use this modular path. So just copy everything here. Okay. And please also check if this environment variable is set. This will be the project number we will use in this training. After load this modular, I think this environment variable is set up automatically for you. And you can copy the access to somewhere, probably your home directory. Or
it is recommended to create a directory using your name in your home directory, and then copy everything there. After the workshop, and please back up these materials.
Yes. There are some other optional settings, like use a little bit different format when you display the queue. And this one also some at least for this long command we need typing a lot during the workshop. So now we can try SQUEUE. It will list the queue on Leonardo. So after setup, we can sort the partitions, some priority tabs or something. And you can also have this S info, it will list the available resource on Leonardo Booster. So this will be the partition we will submit job to. And here it lists the total number of nodes it's available, and some allocated and some idled. So if that's good, the many nodes are idled, probably the job we submit to the queue will run faster. And then there is another queue called serial, this one. Each user will maximum have 8 CPU used on this queue. This is a one login node that they change to the serial queue. Have 64 CPU, and only for the serial work. If you submit the job to this one, I think it automatically change your CPU use, force you to only use one core. So that's a thing probably you need remember in heart. So I think this is the basic setup for the hands-on. If anybody have a problem, please raise hands or write in the chat. So on the title list, we have a similar, probably the path is different, a little bit different. So we can also check this variable. So on title list, this will be the project account used in all these 3 days workshop. And there will be a reservation note for the afternoon training. If you use this command, all the jobs submitted will automatically assign to this reserved computer resource. See, as the control, so too many. Yep. This will be the This will be the reservation for today. It's a start from 1 o'clock to 18 quarter past 18. So I think everything is set up. Let me also copy the access. Oh, now I will go through a little bit about the folder structure for this access. We will have 6 hands-on, and these 2 files will be used to submit the job to the queue, and 1 file for set up the OpenMP threads and something related to the parallelization. when you execute the code. And in this folder will be some solutions, but I suggest we follow the access step by step before goes to see the solution. So looks like no one has a problem for the setup. That's good. Yep. So in the morning part, Professor Levent gave a very nice lecture about EMTO. I think probably now you may know a little bit more about the method and the background. And this afternoon we will really to put our hands on this code and try to run some exercise. So for the EMTO code, we have 5 sub-programs. They do different things. We will see there are 3 listed here. The BFDL structure and the shape. Typically, mainly they are related to the crystal structure or lattice. And the KGRN will do the self-constant constant equation, get the ground state full charge density. And this full charge density will be used to calculate the total energy in the KFCD CPA program. And all these 5 programs have some dependency for their execution. So basically like the VMDL and the KSTR, they are needed by results needed by the KGR part, and the shape need the KSTR result to grab some information from KSTR. Basically, it's about the lattice information, and the final one to give the total energy, the KFCD CPA need all of 4 results from this calculation. And the how to run this code is very simple. You give the executable name with this it's called less, and the input file. So now we go to the first access to run this code. So let's cd to the 00. And if you use tree command, you can see what's in this folder. It's file subfolder for different program and input input file in it. And please try to execute this all of these input files. There probably some error pop on the screen, but don't worry, just random. I will not set time now. No, I will set 2 minutes. Let's try, but don't worry about the error pop up. And after 2 minutes, I will do some demo for this access. Yeah, we run the program on the login node. This should be run very fast, but I think now you will meet errors. Yeah. So maybe 2 minutes is too long. I'm not start to do some demo. Let's start with the VMDL. So after we load the workshop, I think the EMTO code will be automatically loaded. The BMDL will be in the path. So you can add BMDL in this input file. From the name we would guess is for the FCC. So you will meet such error. It says cannot open this file and no such file or directory. That's it's one of the common error will be met if you forgot to create the folder. So let's try again. Yep. So it should be very fast. We can add a time in front to see this BMDL probably take no time to run it. So now we already know the common mistake we could make. So I will not demo the error. So it needs a folder called SMX, ASTR. Yeah, 7 seconds. Oh, it's also fast. Now it's for the KGRN. We need two folders called the CHC and port. The same thing. I can run. But before you run it, there will another file set up the parallelization things. Here, it will set the stack size to unlimited and the stack size for the OpenMP to 800 megabytes. Maybe we don't need so much, but it's a pretty safe setting for this hands-on session. And the version EMTO you will use today have 3 levels of parallelization. So, but the input file doesn't get any further benefit from deeper OpenMP parallelizations. So we set this active level to 1, and the number of threads here we can set 1 because the copper case will be very fast, and the MKL is linked to the thread library, but we don't need such thing, so we set it to 1. And here we probably assign all the possible setted OpenMP and MKL environment variable to make sure nothing strange. And it will show the variables after setup. Oh. So remember, always source this file, make it work. And now we can see the code is running now. Yeah, so 12 seconds. Let me check. Oh, good. It's print something on the screen. We will see how to control this screen output to make it silence or print out. We see they print the total energy with different exchange correlation. Probably I will explain a little bit later why we have so many exchange correlation for one calculation. I think now we successfully run the first access. You are already know how to execute the code, and after that we are going to go through the input file. Some important parameters we should change, or we often change during the calculations. So we start with the KSTR. So the input and output are always important. I think we need to know where to find the output file. So this job name will define the output file names. Also here the dir001 point to this folder. The output, the slope matrix will be stored in this folder with a name called fcc.tfh. And this dir006 we set to the low current directory. So the output print will be in this folder with the name called fcc.prn. So let's go back to the access. We can use tree command again to see what's the output file looks like, structure of the folder. So each program will generate a PRN file and some binary file in some folder. Like we go through the KSTR input file, we see the job name. Also this dir006 means the current one. We are running under this KSTR, so this will be here. Okay. No problem. So you only ask everyone about the login problem for the Leonardo booster.
Yeah, I saw someone got the some error information if they use Windows PowerShell to log in the Leonardo booster. So if you have some problems like this, try to use this login 01-ext instead of login information.
Yes, you can also try this same with 02, 05, 07. So yep, let's go back here. See this SMX folder generate a slope matrix binary file we cannot read, but the PIR file is a human readable. So similar to the rest for program. So always have PRN, some binary file saved. And in the KGRN, there will be a CHD file, that's the full charge density. And some port file. This one save the potential parameter, potential, not parameter, the whole potential during each self-constant iteration. And this file will be needed if you restart this calculation when you need it. Maybe the code not converged or sorry. question. Did you have this SMX folder created? This name? I saw someone ask a question. Oh, yes, David. Thanks, David, answer this question for me. Yeah, let's go back to the KSTR input file. So here, as we need to provide the lattice information for the code. So the one place to provide such information we can consider in the KSTR. So there is a RAT, maybe short for the lattice. Also, some level decide the symmetry of the structure. So for FCC, EMTO should be signed this to 2. And if you want to know other value available in the EMTO or the private lattice, I think I have a link here. We can open the online menu. Let's go to the KSTR, and here list our 14 private lattice available in the code.
Wait, to me, your terminal, your web page,
Oh,
because
okay.
font size too
Wait.
small.
Better? Yeah. So you can always go here to check the input parameters and remember the recommended value if you don't have special needs and try not to change them. Yep. Let's go back to KSTR and how they describe the lattice. Here, 3 line for the BSX, BXY, and BSD. That's for the translation vector defined the lattice. And this A, B, and C, they are value renormalized to the length of the first vector. But this is for the conventional setup, the 3 vector define the conventional lattice. But here as the one you set up here, like we choose the RAT equal to 2. Even you give this value explicitly, but you should also always remember EMTO has its own internal definition about the orientation of this translate the vector of this Bravais lattice. This are tricky or some part you need to remember in mind if you give arbitrary setup, it may cause problem. But for this access, I provided the input file for all the access. So let's don't worry about this for now. And also want to mention this coordinates for the sites or automation. Maybe we call it sets. It's the Cartesian coordinates. It's not fractional coordinates. That's very important to remember. Okay, well, so the BMDL input file, we can see they're quite similar to the KSDR for the lattice information part. Yeah, I forgot about this. It's one side, only one, and here it's 0, 0, 0. Remember the KSDR and the BMDL, they must be consistent or describe the structure. And in the shape input file, we provide. Oh, I am not. I finished. Yes. Here I'm also asking what to do after KSDR. Yes. You go to the KGR, do the same. And don't remember source that OMP file first. So I think you can always go back to this dependency graph to see what's next to run, like the KSDR BMDR shape. So if you run KFCD, you need KGR and be calculated. So follow this flow. I think you can solve that problem. Yeah. Let's go on. Here, the shape input file. You provide the name, so it's point to the output file from the KSDR, and this is really place to decide which lattice the shape function will be calculated. And for a good practice, the job name should be consistent with the file name. Otherwise, the output file and the input file will be a little bit confused. You have different names. Yeah. And come to here, we will probably find out all of these three are only related to the lattice information, and you don't provide any elements or chemical things. Also the size of the crystal structure. So that means all these three defined for this lattice could be always reused if you need it in the future. If we found it's a little bit relative time consuming, like 7 seconds for this input file, but don't worry, if you run a lot of self-constant calculation with this structure, the 7 minutes will be averaged to 0 for rest of other calculations. So the KGR input file for the inputs, we see it's need the KSTR results, also the BMDL results, and this job name, always remember that. And you have a port folder, you have a charge folder. So if you don't have them, the code will complain about that. And how do we decide the size of the structure? I mean, the lattice parameters or something. So in EMTO, we use our average spreader about the weakness cell. So that's here I have this example how to convert them to the cubic conventional cell lattice constant. Like in the BCC convention cell, we always have two atoms. One is for the corner, one is for the center. So we think this Wigner size cell will be per atom radius. So this volume should be same as the cubic of the lattice parameters. So you use this to convert to the Wigner size radius. And in the EMTO, the units for the length, we use Bohr. And I think normally we will got Armstrong for other code or from experiment. So this units converting, you need to take care by yourself. And also for the energy, we don't use electron volts, we use Rydberg. So another important input is this IBZ. It's probably is short for the irreducible Boolean zone. The type is consistent as the KSTR LAT value. So you need to take care about this parameter. So the value you could find also in the menu, just check the KSTR LAT options here. So there always be some convergence criteria set up in the density function theory code. Here is a tolerance for the total energy. There tolerance for searching the Fermi surface, Fermi level, sorry, and also tolerance for the CPA convergence. And this inter equal to 50, that's for the upper iteration limits. So your code should be converted in 50 iterations. But if not, you probably need to increase this value. So when you match this convergence criteria, the code will be stopped. Also, another is if you go to this maximum iteration value, the code also stopped. And here we saw we put the real elements onto the lattice. And in the KSTR, we have one site, so it's for the IQ. So for the first IQ, we put the copper, and there's the concentration is 100%. We will talk this later in access 04 and 05 to do some alloy calculation with CPA. We will go back to this, come back to this parameters. And in the end of the input file, there is a valence electron configurations or atomic configurations for the copper. So the valence we have one is for consider this orbital like a valence electron. 0 will be the core electron. And here EMTO use a green function method. So they integrate the green function with a closed control, and the singularity or infinity will be if the green function is correct normalized, each pole or the singularity will be counted as a one electron. And we in the code there is a settings for this called Z match equal to C. It use a semi circle control. And the mesh point on this contour is exponentially distributed. That means in the close to the Fermi level, they will be much denser than the further parts. And this NZ0 means in the beginning of start, the calculation will be 6 point on this contour, and during the each iteration, it will be increased until to 16. And this EMTO code also monitor the convergence for the Fermi level. How to search the Fermi level for this closed, except this closed contour, we have some horizontal contour near the first points of the semicircle contour. It's like a wing both sides of these points. And we have this parameter called EFGS. That could be short for guessing for this Fermi level. I mean, the code start from charge density for isolated atom, and we guess a value where to find this Fermi level, and this HX is the step for this small wings, and have 5 points. Well, distribute both sides. So this value should be always odd number. So make both sides have similar number of points. And this CRT parameter, I really don't know what it's short for, but this has a two option, like capital M and small m. That means we monitor the Fermi level convergence for the metal system. And this big M and small m difference could be because this small contour will be decreased during each iteration, and this step size HX will shrink during the calculation. So for the bigger M, this shrink speed will be a little bit slower than the M. That will help for when the initial part test is not very suitable for the system, and have more searching range during the first few iteration to find all the electrons. And another parameter, when you set the dots equal to D, will calculate the density of states, but we don't usually need turn it on. So, and also when you plot the density of states, this NZD will control how many mesh points on this dots calculation. And the definition of the Fermi level means all the electrons should be occupied. So the area of this density of states should be the number of electrons. So that's how EMTO code searching for the Fermi level. And I think this will be our important thing because you will meet some errors when you do the calculation in the future. But when we met such a problem, you always come back to this figure to think about how we search the Fermi level and why the code may stop. Sometimes the initial guessing is not good, and the valence electron may be outside the searching energy window, so that code stopped. So I will not say more about this. I think for now you have a general idea about how to run the code and some of the important input parameters you need to change. And I think this will be enough for the rest XS today. So when you meet a problem, you can always come back to this first example, 0, 0. Yeah. Yeah, probably I take too much for this. And the next is second, I mean the first real axis. So we create a conventional setup for the copper with 4 sides and make the calculation. So the first step, copy all the input file from the first example to the second one. So it's MP minus okay. 1. Okay, goes to 0, 0, 1 and remove the output. Wow, it's not really big. Okay. Let's remove. Now it's cleaned. Now we go to the KSTR. So for the FCC, now we create a full set conventional setup. So the symmetry or the lattice will be changed to simple cubic. And for this translation vector, it should be the diagonal one. I think this will be same as any other DFT code. So we have.
No, wait, I think the BSZ should be 1 instead of QZ.
What? Yes. Yep. Also for a BMDL. Now it's a little bit different as we have on the training material, but don't worry, we delete. So that's another representation for the structure at here. we make it consistently, use this I prime equal to 0, and copy everything here. And we didn't change the output file name, so the shape input file should be same. So same trick. So run the input file. What happened? Yeah, that's a PSTR equal PSTR. Oh, so wrong. What? This always happen if you manually change the file. We can always diff it. Yes. That's the 4 atom. We didn't set the atom. We forgot to put the atoms there. So we have another 3 atom. It's for the phase center. It's good to have problem. So also need the same number of lines for this A over W. Let's see if it probably not right. Bigger. Good thing is we have solutions. Mistake. Uh-huh. I really typed wrong here. It's diagonal 0. The sequence will be different, but should be okay. Yes, now it's running. I saw the chat. Yes. For the question on the chat, you need to source the OpenMP setup is here. So if you don't source this, probably you use all of the CPU on the login node. You see here, it's use 128 threads in OpenMP level 1. And that's a thing you didn't do. You need always source this file. Then we can also change this value to 4 to see if the KSTR helped. Here, we have 4 sites now. The KSTR run much longer. It's like 27 minutes, seconds. So we source it, use 4 threads. It's down to the 8 seconds. Almost scaling with number of atoms. But 27 seconds is not long. Probably use 1 thread, so it's always okay. Now go to the VMDL. So we need to change this consistently with the KSTR. These lives here lead to the rest. They are fast. Now it goes to AGRN. So we have 4 sites in the KSTR setup, this convention setup. So here we need to put for cover on these 4 sites, for first, second, third, and fourth. And this IT means the equivalent site, because this is a FCC lattice, all the sites should be equivalent to each other. We don't set other value. But if you don't know the symmetry or they are equivalent or not, you can always give different value. But remember, if you give different value here, this NT, you must change correspondingly to 4. And if you give 4, you'll need repeat the atomic configuration for 4 times. But we know it's equivalent, so we only set to 1. That's means problem wouldn't be this fast. Yes, we forgot the ABZ. We use another setup for the simple cubic. So getting. Have you sourced that file? If you didn't source it, it also always show in 128 threads. That's for the question in the chat. What I'm doing? Ah, yes, the IVZ. This value should be consistent as the KSTR. Now we run the code. You see, if you source that OMP, here will be consistent with that OMP file setup, like use force rights. And on Zoom, I cannot really interactively. So, yes. CD. I think we don't need to change. Oh. Now we go to the KGR and see how to confirm the calculation is really converged or not. We can grab the ERE from this output file. See the print each iteration, the relative error for the energy, also for the Fermi level. So we set up the convergence criteria to 10 power minus 7. So here we see it's converged. And you can always search this converged in the ERN file. It's summarized like 20 iteration, it's converged. And also this number of states in the output file. So this four sides, each of them are copper with 11 electrons, so totally 44. And this NOS is calculated from the dots. So they should be exactly the same. So that also means the calculation is good. No. I think for this question, you probably should diff with your input file with the, let's see, is this the which input file you use for the 001 access, or back to it's called finish. INS yarn. So the last line of the output file has this finished. So you can always check with this command. The first is converge number of states and finished. finished for the PR file. If it show all of them, probably the calculation is good for the self-constant loop. Let me answer this question for Leonardo in the chat. He said it's for the KSTR, BMTR, and the shape. Did any other people also meet this problem, or just Leonardo? Let's see the KSTR. So make sure they are always I mean aligned. The input file for EMTO format is very strict. I'm not sure. I couldn't see exactly your input file, so maybe I can't show it directly, but you could do the diff to track the input files if they are aligned rightly. Or I can come back to you during the coffee break. Solve that problem, because the next access doesn't really relate to this one. So I think for the second access, the takeaway message is you can use this command to check if the KGR run finished correctly or not. So it's first is converged for the energy and the Fermi level. The second is the number of states, they should be same. And the last one is this calculation finished really. At the end, the last line has finished. So I think that a good time to make the coffee break.
Sure, we can take a coffee break.
Yeah, and probably I can solve the problem for the friend called Leonardo in the chat. Do I
Let's say for
did him need my help or not? Maybe I
minutes.
send him message. Uh, how, for how long we take coffee break? Only
Yeah, 10 minutes.
10 minutes. Yeah.
Yeah.
Were there some questions on the CAMD? I'm not sure. Oh, maybe I answer questions later. For there's some tricky question here. For the last one, the master ST, the multi-scattering code, take care CPA. I think they should have full potential implementation for the mask code. Or if they don't use full potential, I believe they are KKRA level. Probably not take care about the overlapping region precisely. still on the second generation KKR method level. So the elastic constant or other non-closed packed structure, maybe the total energy not accurate, but this is my guess now. I haven't tried this code yet, but if they are full potential CPA implementation, then I'm not sure. Yeah, you can after this hands-on, I think you can set up some comparable examples to make some benchmark to get your own conclusion. Yeah, so for the question about this chromium aluminum iron alloy, it's 400 chromium-based alloys. What I can say, so you need careful about this alpha CPA input parameters, and probably for such alloy investigation, people usually focus on the trend, not the exactly values. So except the alpha CPA value give you total opposite trend, I think you can trust your result on some level. I mean, you probably want to design such alloy with some or predict properties using CPA. Maybe after the 0004 access, you can do this calculation by yourself. Also, yes, EMTO don't have force, and you can make some local relaxation with the compared to the energy. Like for the surface, you can always manually relax the first layer ultimate interlayer distance. Also for the stacking fault, it's also a planar fault. So maybe the local relaxations will reduce the error, or you want to compare the results from EMTO and other DFT code like VASP, you can compare with the unrelaxed results. And for the relaxed one, as I said, it's always focused on the trend with alloying effect. So unstable stacking for the energy, I think we have several from 11th group have several paper about this. You can read this paper and see the results if the accuracy is on your required level or not. Yeah, the high throughput manner of EMTO code. So I think after the hands-on, you are much more familiar with the basic setups, and you just need to change a little bit the input output names or something much easily for you extract the results. And I think during this hands-on, you will meet several typical errors that crash the code. So you know how to change it to the right value, get the right result. And from this graph, you can easily check all your calculations correct or wrong. So to generate the input file with a programmable manner, you can do it yourself, or you can use there is a PAW-method, also CIF to cell. They also has some limited support for EMTO input format, but you need careful about that. I think this hands-on, the importance is you know what should input put into the input file, and what you can grab out and make sure the calculation is right. So for the high throughput or workflow, that's different people have different ways. Yeah. But if you're really interested, we have one solution. You can contact me after the hands-on. So that's all for the question. Let's go back to the access. So there one more thing left for this. There one access is the total energy calculated here. We can grab the total, give this dash upper PRN. So we still there are different exchange correlation. They are calculated on a perturbation way. It's used ground state charge full charge density calculated from the KGRN, and based on that, use different exchange correlation to get the total energy. And here we could compare to the one to the first axis. There is we use a different lattice setup, but they are both with center cubic, so the total energy somehow should be close to each other. Now we can see the little bit difference for this perfect energy. So the reasonable guess is we could play with the K-point setup. So in the training material, I gave some suggestions for this K-point convergence test you can play with by yourself. And the next exercise, we will calculate the equilibrium volume for the FCC copper. I think that's important information for any DFT calculation. For example, if we calculate elastic constants, we must provide the lattice constant information. So how could we get it? We use experimental value, or we predict it with the DFT tools. So here we will do such access to get the lattice constant for copper. So we choose some equation of states, fit the curve, like the energy change was the volume. So here in the EMTO, we choose this called MOS function. The energy as a function of Wegener access radius. And the basic thing is that we change the input files with different Wegener access radius. So as I said in the XS00, we can always reuse the same setup for the same lattice. This should be the 02. Yeah. So you can use LS and SS. These three folders point to the first one we used. So we don't recalculate them anymore. And we also copy it. Yeah. Oh, I'm not sure you are familiar with the seed command. So this is like use regular expression, match the patterns, and make some change. So this S means substitute and separated by this slash, and the point means match any character, and star means 0 to infinity number of character in front of it. So this match anything, it means the job name after that match it, and the change to another one. We calculate the copper, and we set we can access radial change from 2.6 to 2.72 with step with 0.02. And the job name will be substituted with the new values, and the SWS will be take each value from this sequence. And they change the copper date file from the first one and output it to the current folder with the KGRN. So keep the job name and the file name consistent is a good practice. So let's see, and we can always put such a thing in a file, make it like a script, and we can run it. I will not type again, so I can copy the one I made before from the solution 02 solution. And we see basically we do the similar thing. We use the KSTR, make these links, and create a folder KTRN, and also the safety and port for the different SWS. We substitute the job name and Wegener access radius based on this the first access input file for KGRN and to the current folder, similar with the KFCD. So Notion, you see the executable. No, we can. Why? Because we already linked the folders yet, so we comment it. Is that the problem? Let's see. Yep. So verify one of it. Let's see if it's a problem or not. It should be changed. that we want. Yes, let's change the job name and weaknesses rating. Wait. There is a problem in the chat. Maybe I come back to these questions later, actually. So I think only one people met this problem for the NQ. So you should check the KGR and NQ and no, the KSDR setup. I think this is the four-side conventional cell FCC. So that one have four sides. So in the KGR, and when you write down the elements, you need also four, like here, and you need change the IQ for different value. So find elements on different site. It's like 1, 2, 3, 4. Yeah. For come back to this example, I think we already successfully changed the weakness size and the job name. Now we need submit the job to the queue because there's a lot of calculations. I think you can manually batch. Oh, I think let's come back to this file. I think here EMTO.splash file. So on the Leonardo already set up the count number here, and time limit 30 minutes is much is more than enough. Also, we use one node. This minus T means one core, and here we use a job array. You can set it to how many of data files here, like so too much to explain what's here, but we can learn it by use examples, like we batch minus A. Let's see how many data file we have. 9. Okay, so batch minus A 1 to 9, and this is 1 copper, so use 1 core is more than enough. And with this EMTO spec file, no partition spec. Oh, okay. Okay. So the default partition which goes to this serial. Oh, I think the optional setup we have. Wait. Oh, yes. This is finish. Yeah, we use 1 core is more than enough, but on this serial partition, they turn on the hyper-threading, so it shows to CPU, but we only use 1. And there is a max number of jobs one user can run in the same time. I think you can only run 4 each time, but the code runs fast, so no problem. Here is the command to submit a job. Oh, will be done. If we remember how to check the code, we use grep the we use egrep right here. Yeah. Pretty every calculation is finished correctly. Oh no, that should be how many lines? 28. No, there must be something wrong. Each should have 4 lines and we have 9, it should be 36. So I warp a command for you. Check all the here. It shows the not converged one, and also they are not finished. So let's see what's the problem of these two. Fermi level not found, and the first iteration finished and Fermi level not found, and this may cause by many reasons. So let's try the easiest thing, like we decrease the mixing for the calculation. That means each iteration will take more, I mean, some percent of old charge and the new charger mixed together for the next iteration. So maybe 10% is too large. Let's see if 3% could help. Oh, yes. So there is a message level. If you set to 1, it prints something on the screen. So we run it on the login node. That's not a very good thing, but it's fast. We can do that. Yeah, it's runs. Get past the first iteration. That's the mixing is the problem. So here we use this checkout command. Oh yeah, you need to get the PRM file. Yep. We saw one, probably there is another one. I think it's the same problem. We change this copper dot the mixing to a relatively small value, 3%. So check on, no, same. Yeah, everything's good, no bad NOS, everything converged and finished. So if you want to know what's in it, you could open it. So just warp of 3 thing. Let's open one, like check converged. So this capital L will list the file name which not match this thing. So no converged file. So that's the trick. So for the NOS, we grep this NOS and make some value difference with the 5 column and 8 column, and use this square of the power tool, like instead of a absolute value. If larger than a tolerance value, we print the byte NOS. So that's a simple script you can check your output. So people ask about high throughput computing. I think check the correctness of calculation is important. So this is a basic gradient for you. So go to the KFCD, similar command to submit a job, dash me. You see the four start immediately, simultaneously, and there are four in the wait. So that the max job you can run. So maybe I'm too slow for the hands-on. So the non-guided tutorial probably become a guided tutorial for the next 2 hours. That's this for the UI. Oh, it's done. So we can choose one of the exchange correlation. We see the energy per side and also the weakness radius. So we should feed the equation of states for these two columns and get some results like this one. So for the fitting, how to fit a thing, you can implement in different way like Python or something else. For Cavania, I prepare script for doing this, the KFCD. Oh, it's empty. What the problem? Oh, it's, we should go to upper level, like EOS or the 0, 0, 1 or 0, 2, right? Yeah, it's a feed the most function. Let's choose the PBE for this folder, equation of states, and this is the equilibrium volume, Bach modulus, and this is the fitted lowest energy, and some quantity for the fitting. This should be the R square. And also in the KFCD folder, there is a figure plotted. It should be look like this. And now another thing I want to emphasize is in the KGR calculation, there is a called soft core. This should be used as one. The frozen core is used a long time ago, and the core electron density only calculate once in the beginning and keep same in the during the self-iteration, and this valence and the core interaction doesn't take count. And so for more physical reason, we should always use the soft curve equal to y. So I make this on purpose for the example to let you remember always use y, and you can practice with this y setting for the equation of states and to see if the equilibrium volume and the Bach model if it's changed. So that's for practice for yourself. I think you could change the value from the first example input files, and they will take for all the input file generated for equation of states. I think we finished the second one, and is another time to take coffee break, or we can go on for 50 minutes after that of coffee break?
You can continue probably after 15 minutes. We can the participants to play the code themselves.
Sorry.
Yeah, we can ask the participants to do the following exercises themselves because they are not guided, and
probably.
or if you have time, you can stay in this room for a while.
Yes, I think the next one is a relative important because we will first time to do some CPA for alloy things.
Oh.
So maybe stay for 15 minutes.
Yeah.
And the rest we can do it later.
Yeah, sure. Please go on.
So there more than the elastic constant calculation. So mainly we use the method to deform the lattice, and with this corresponding energy change related to the distortion, we calculate the elastic constant. So how to deform the structure. So the input file we already provided in the third example. You can see this, and as we said, it use another presentation method for EMTO for the structure, like this should be the face central orthorhombic structure with zero distortion. It should still represent the FCC structure, but from here we only saw the 3 angles between the transition vector and this POA COA value, also the basis atom. So that's not too much information there, but you can always see the output file. Now it's a way to know how EMTO defined such structure internally. So the FCO for the all ABC equal to 1, it's similar as the FCC thing or BCC, and 5% you can also get it from the output file. Yeah. What it looks like. The rest thing is for the KGR input file. You need use all these deformed input structures and different with the equation of states calculation. Now you change the structures for each calculation. Keep the same equilibrium volume calculated for all the deformations. The important information takeaway is we choose such a distortion. It's volume conserved. That means the volume didn't change during the deformation. The good thing is volume doesn't change, the weakness radius doesn't change. So also the radial mesh doesn't change because of that. And also all these deformations, we could only have the even orders, so we don't need calculated positive and negative both. We only calculate one side is enough. And if you can apply such a deformation on FCC structure, easily detect them with this symmetry loose for lower symmetry lattice like the FCO and the BCO. So for the KFCD input, you have only the job name and structure need to change. All the input file, I think, it's already here, and you can manually submit the job like before. But you can try this script to do that for you. You give a folder name like you give the folder name, you submit the folder. So sub the VMDL. Yeah, they're very fast. And after you submit the KSDR, you see they submit 2 jobs. So one is the KSDR, one is the shape. That shape need the KSDR, so it become a dependence. So this script warp everything, reduce your human labor. Yeah. Okay. Otherwise, you just submit all the job one by one for each folder. And the dependence only show the ones like a K, SDR, and shape, or KGR with KFCD. So still not finished. Wow. Yep. So the KSDR and the shape done. So you sub the KGR and that way. The elastic constant calculation use a relative high K points, so the calculation will be take much longer. If you use only one CPU, that will be too slow for the demo. So we can always cancel the job with dash me. So when you submit the KGRN, you can give the -C like 8. It will use 8 core automatically do the calculation. Let's see, CF means the job is started, and use 8 core, all the while jobs is running, and all the KFC is waiting for the KGRN finish. So for this access, suppose we expect the results like all the deformation calculation finished, you grab the total energy. You will see how they change with the deformation, and the deformation is take 1% for each. So the string square will be you will calculate this square. We take the first energy as a reference and fitting the shifted energy curve like this. The slope will be the elastic constant. Calculation takes time. So this will be a little bit different on the title list, but the command should be the same, like submit a folder. You can give this -C with the CPU. I mean, otherwise, you need to submit one by one. Too late. Too time consuming. Yeah. Yep. That's finished, and we always check our AGR and all the output file. Oh, good. I think it's good. And if I remember, then I also gave a last think bit for 03. Yes. Another script fitting for this elastic constant. If you want to check, there will be figures in the fit folder with 2 figures. Could be similar as in the page here. So the elastic constant calculation is done. So next, related to CPA, I will go faster, and let's finish this thing. And we calculate some mixing entropy for BCC iron chromium system with the ferromagnetic states. So the story probably here you can find in this link. It's an old paper from 2006. What we aimed for is to repeat this figure. Is that too small? No, much clearer. So we use that formula calculate this mixing entropy and plot the figure as a concentration. So it's take the reference structure like an FM ferromagnetic iron in BCC structure and non-magnetic in chromium. So this is just the practice, and we are not describing the scientific problem. Yeah. So we need calculate the equilibrium volume and the corresponding energy for each concentration. So before we change the concentration, we create one input file to make it works. So we change the job name, and this is the BCC. So I already prepared the BCC input file for this example. Did I? Oh. Yes, here the BCC input file for the KSTR BMDL shape. So you probably need to create this input file from the copper case and make some change. So the difference here is we put iron and chromium on the first side with concentration 50-50, and we give an initial gas for the split, the initial moment, magnetic moment for these two elements. So they are occupied on the same side. You just change the concentration here. So you also need to provide the atomic configuration for iron and chromium. So probably this is the diff with the copper and what happens here. So the copper changed to these two, and that's weird. That's these two elements related input in the end. Don't forget to change the structure. Yes, this is for the BCC, and this is what should be prepared by you for the KGRN and the KFCD. Probably for save some time, you just copy it from the solution. Therefore, KGRN, iron, KGRN, maybe. It's the same way sub the BMDL, KSDR. After the finish, we fire up the KGR. It's time. KGR 38. So this is just warp something on top of the setup and decide how many data files in that folder and make sure there is a dependence uh, like after finish one job and to start another. So totally depends on yourself what you want to do. So for convenience, we provide I provide this script for you. So nothing relate to the EMTO itself. So I'm check the PR file. I see it's not converged. Also show abide OS. Why? Let's see in the KPR why it's not converged. Let's grep PR. Okay, it's reach to the 50 iterations and the energy didn't goes down. The relative error always 100%. So what could be solve this problem is old trick decrease the mixing. Let's see if this helps. Go back some the KVR. It's 8 core. So this script take care if you use more than one core, it goes to another partition. Yeah, so check again. It says converged. It's nothing not converged. It's finished, but still bad number of states. So let's see what's the problem is there. Let's go to the end. And, we saw here something like the CPA equation for spin 2 not converged, but spin 1 is converged. I mean, in the 7 iterations, some is converged in 3 iterations. So this could be the problem is the CPA loop not converged. So we could increase the CPA to solve this problem. Let's see if it works. Like equals to 14, 17. So same and math. We can check your how how long it usually takes. We can read from the SLR mount file, output file. It's like a seconds finish. Oh, yes, KDR finish. Let's see. This time is a word convert on. Yeah, so it's bad OS gone. Everything is all right now. So we finished first step, create a correct calculation for one concentration. So we need to calculate other concentration, all of them, but also with a different weaknesses radius. That's how we get such a curve. So we can combine the equilibrium volume scripts from the 02 and add something to change the concentrations. So a new command for seed is like you can point this change on specific lines. So 28 and 29. So we change this 50 to some value we want. We take a more dense point below 10 and some points about 10%. And this is for the chromium concentration, like the figure here. Also, to make sure it converges, we increase this maximum iterations. And this script is also in the solution 04 FM. Yep. And wait for this FM. Oh, how to read here. Yes, it's should be put in the upper folder. No. So let's generate all the input file for different concentration inside this folder. Each one will create 6 different volume for its concentration. Reuse the KSTR shape and BMDR from under this example. So you can always submit them. Now we can loop to do this like iron stuff. So it's submit the KGR folder to sub.sh.i minus C8 9. So we just wait for the results and feed each concentration with the most function, get the lowest energy. So this fitting you can do in any manner you like, or you use this provided script with it. So they need wait into the queue. See. Mm. Oh, somebody try something with mono. By the way, the EMTO code we provide for this training is only OpenMP parallelization, so no MPI in it. Across the road knows probably a problem. I'm not sure what it's doing now. During waiting for this result come out, we can quickly go through the next access how we create a system with paramagnetic states. So we can create the spin up and spin down as a fake alloy fashion. So we do half percent of this errand to spin up and the other half to spin down. So that's to mimic magnetic disorder states. So everything is similar as the access 4. And here is the key points. We split the iron to 25% and give the initial gas to spin up and spin down. So we have 4 elements on one side. So this a maximum number of type of atom set to 4. Don't remember to change that. And don't forget to change it. Yeah. And also we added the atomic configure for extra elements. So that's the trick for mimic paramagnetic states. And the third axis will be calculated diamond structure. It's a relative complex structure, but it's still FCC with 2 basis sets shifted along the diagonal from 0, 0 to a quarter along the diagonal. So here is the ASTR, and maybe after you run it, don't forget to check the warnings in the output file of KSTR. It complains about big overlap. So what this A4 structure looks like. So here I introduce to you this website. one of my favorite place from the A-flow. Show the structures. And you can see for this A4 structure, the diamond structure, there are plenty empty space in the unit cell. So if we think the linear overlap, how it calculates like the whole volume divided by 2, and also the distance between these two atoms, how the relative value, like the sum of the weakness radius of these two divided by the distance between these two. That's could be very large overlap if there are much empty space there. And one more thing I want to emphasize is usually these days people use them called standard primitive cell setup. So they form a standard way of the orientation to express the primitive cell. So this one is maybe different with EMTO. So when you try to input the information for the KSTR, you should always think about that and convert it by yourself and put into it. So this one is like missing the X, missing the Y, and missing the Z. This is for the FCC lattice. If we go to the what we are missing is first missing the Z and missing the X and Y. So there's some difference. And how to make this space more fill up or more close packed structure. So we could add another two sides for half and 3/4. So what lattice it could be? So I couldn't find something. I mean, for 4 sides with same elements, but I found this one is a Husserloy L21 structure with similar shifting along the diagonal, but put different elements on it. But it doesn't matter. That's the same thing. If we put the same same elements on it, it will be the structure. So that's the number 6. Oh, number 6 could be created by hand, but we don't have time to do that. So you can always copy the solutions 0.6, everything to the 0.6. And we created this A4 L21 structure. Also another one we will show you later. Also the input file for the carbon in diamond structure. We see the KSTR L21. So the NL we choose to 3. That's could be what's the reason? Is like we don't need so many orbitals because the carbon is only have S and P electrons. And this setup could be save some time, but if you give 4, it's also okay. So that's a thing like how we reduce the basis site in the EMTO. So in the cage, yeah, we take a review this input file for carbon. That's we said we get extra sites, but it's not diamond. How we filling up that empty space, we use this called empty site for this extra tool. And you see they don't have really have electrons there, and they are include in the charge renormalization. So this empty is very important when you fill up the space, make it more close packed. More attention to that. I think we come back to the sports thing. This time it's in the FM folder. AGR. No. All the concentration, KGR, all the output file. Yeah. We'll have guide NOS. You can play with the mixing. I think that's the problem. So you can make some change and regenerate the input file and make some practice. I think the hands-on session, guided hands-on session will stop now. And if you have any trouble to make some practice for these examples, you can stay here and ask questions.